Hello everyone, I'm Partho. I have made this video for every physics student who studied physics, who is studying physics, and who is going to study physics in future in class 11 and 12. This video is for every physics teacher who teaches in the elementary level. Because this video is about the misinterpretations of Bernoulli's principle. I have watched several YouTube videos of physics classes and I have found that all the classroom demonstrations of Bernoulli's principle are wrong. In all the physics textbooks of class 11, the examples showing the application of Bernoulli's principle are wrong. First, let me show you a few demonstrations that you might have learned as applications of Bernoulli's principle. If I drop the cylinder made of paper from a certain height, it will go straight and hit the ground. Now, if I give a slight rotation and drop, what will happen? Let's see. See, it rolls back. Let us say it again. This happens due to Magnus effect. But in the most of the textbooks, Magnus effect is explained in terms of Bernoulli's principle. Next, this is a piece of paper. If I blow air above this piece of paper, the paper will rise. Let's see. Now this phenomenon is also explained as an application of Bernoulli's theorem. Now this is the next one. If I blow air in between these two pieces of papers, common sense tells that the two pieces of papers will move apart. Let's see what happens. As I blow, these two pieces of papers come closer. Now this phenomenon is also explained with the help of Bernoulli's principle. You might have learned that the phenomenon of rooftops going off during hurricanes can also be explained with the help of Bernoulli's principle. Now let me tell you that all these demonstrations are wrong. Now before explaining the demonstrations one by one, let me discuss what Bernoulli's principle says. In a steady flow, the sum of kinetic energy, potential energy, and pressure remains constant along a streamline at all points on that streamline. Let us consider a fluid is flowing through a pipe having two different area of cross sections. The bigger area is A1 and the smaller one is A2. Now V1 is the speed and P1 is the pressure of the fluid in the bigger portion, and V2 is the speed and P2 is the pressure of the fluid in the smaller portion. From the continuity equation, we can derive that V2 is greater than V1. Now, if we consider that both the portions of the pipe is at the same height, we can ignore potential energy from the Bernoulli's equation and we find that P1 is greater than P2. So from Bernoulli's principle, we can see that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure. For the Bernoulli's principle to be applicable, the fluid must be in a steady flow, the fluid must have negligible viscosity, and the fluid must be incompressible. It feels counterintuitive that when speed increases, pressure decreases. This is because the pressure that we are talking about here is static pressure. It is not the pressure that arises due to the speed of the fluid. We can see from the figure that static pressure is the pressure exerted on the walls perpendicular to the flow direction. It is the pressure experienced by a test particle in the frame of reference of the moving fluid. Dynamic pressure arises due to the speed of the fluid. Now let's come to the demonstrations again and discuss what goes wrong in the explanations. In the explanation of rooftops going off, let's see the wrong explanation. It is described like this. At point A, above the roof, the wind has high speed than the point B, which is inside the house. So pressure at point A will be lower than the pressure at point B according to the Bernoulli's principle. So the rooftop will go from higher pressure to lower pressure. But this explanation is wrong. We cannot use Bernoulli's principle to compare two different streamlines. Bernoulli's principle is applicable only along a single streamline. And also, we cannot equate the total energy inside and outside the house. Total energy may be different at the points A and B. Correct explanation of rooftop going off includes many theories such as turbulence, circulation, which are out of the scope for discussing in this particular video, but we have to remember that Bernoulli's principle cannot be applied here. Now let us discuss about Magnus effect. You all might have seen a curved football shot. You can smash a table tennis ball from a level below the table. You might have seen in volleyball service that the ball which was going out suddenly dips down after crossing the net. All these phenomena happen due to Magnus effect. If a ball is rotating in the anti-clockwise direction and it is moving forward as shown in the figure, it experiences a downward force and it changes its trajectory. This effect is called Magnus effect. Let's see how it is explained in classrooms and some textbooks. When a ball moves in a particular direction, the surrounding fluid, which is air in our case, moves in the opposite direction with respect to the frame of reference of the ball. Now, the wrong explanation says, on the side A, where the direction of the flow and the motion of the ball are opposite, the flow will slow down, and on the side B, the flow will speed up. So, according to Bernoulli's principle, pressure will be higher on the side A than the side B, and hence the ball moves from the higher pressure to lower pressure region. But this explanation is wrong, because the property of the fluid that is used here to explain the acceleration and deceleration of the fluid at points A and B is viscosity, and Bernoulli's principle is applicable only when viscosity of the fluid can be neglected. But in this case, viscosity cannot be neglected, hence Bernoulli's principle cannot be applied. The correct explanation of Magnus effect can be easily understood this way. When a rotating ball moves to a particular direction, the wind flow in the side A will get slower due to the friction of the ball surface and the passing fluid and the viscosity between different layers of the fluid. And on the side B, a boundary layer will form at the surface of the ball which drags the flow as shown in the figure. Now, due to asymmetry of the separation points of the fluid from the surface of the ball, an upward force will be acted on the fluid by the ball. And as Newton's third law will say, the reaction force of the flow on the ball will push the ball downward. That's what explains the Magnus effect. Now let's come to the piece of paper demonstrations. When we blow air in between these two pieces of papers, they come closer. The wrong explanation is like this. When we blow in between the papers, we create a low pressure region due to the speed of the flow, and the surrounding air is at rest, and hence the pressure is higher in the surrounding according to Bernoulli's principle. Hence the surrounding air will push these two pieces of papers to come closer. This explanation is also wrong. Now, before discussing why it is wrong, let me show the other demonstration. In this demonstration, the wrong explanation says, when we blow air, according to Bernoulli's principle, a low pressure zone is created above the surface and the air below it, which is at higher pressure, will push it upward. In that case, how do we explain this? Now I am not holding this paper. I am placing this paper on my two fingers and blowing air above this paper. By blowing air, I am creating a low pressure area above this piece of paper. So according to Bernoulli's principle, it should go off, but it doesn't happen. So how do we explain it? We cannot use Bernoulli's principle here. As discussed in the rooftop case, we cannot compare two different streamlines. And this is not true that moving air has lower pressure than the surrounding air. For example, if we switch on a hair dryer, the surrounding air should have squeezed it, but it doesn't happen, it spreads. Now what is the explanation for this piece of paper demonstrations? It happens due to Coanda effect. Let me show you a demonstration of Coanda effect. How did it happen? Let's discuss. If we blow a free jet near a smooth curved surface, the jet will remove the air molecules from its immediate surroundings. This is known as entrainment. Due to entrainment, a low pressure area will be created near the surface, and hence the jet will deviate and stay attached to the surface. This Coanda effect can explain the piece of paper demonstrations. I don't blame the teachers for these wrong explanations. Many great scientists have done this before. In the Feynman Lectures Volume 2, Richard Feynman has given this example of a piece of papers as a demonstration of Bernoulli's principle. These wrong examples of Bernoulli's principle are going on for several decades now. Let me show you one more demonstration. Now, why did this ball get trapped in the airstream? Write your answers in the comment. Let's see. I want this video to reach every physics student and physics teacher so that no one misinterprets Bernoulli's principle again. Thanks for watching.